Welcome back, guys. Today, let's go through what we did yesterday. So, yesterday we managed to get the spin lock implementation working using the compare and swap plus memory tagging. So, this is what we wrote, and it's almost a simple program that just loads the memory using a special instruction and updates it with a new value, and internally, because it's memory tagged, it's atomic, and we get the locking mechanism based on this. And we also tested it yesterday using just normal C. We didn't test it in our own environment, but today we'll do that. But yeah, overall we have the implementation and the locking seems to be working fine. Today we'll have to overall just not just implement, we also have to integrate this spin lock into our block layer so that certain operations are synced. And then we need to implement the user programs. There needs to be at least 2 user programs that are gonna call syscalls, and internally it's going to, let's say, write to a file, and 2 of the processes are gonna keep calling write operation, and we are gonna see how that is gonna turn out. And that would be the best case scenario, because 2 user processes having the same kernel context are gonna call, let's say, write operation, and they are gonna both go through the same block read or block write operation, and they will be synced using the lock. We can also try to maybe comment out the lock and see what happens if we don't have a lock, and what happens if we have a lock, and I will get a comparison of having the synchronization. Overall, our kernel, I'm just trying to write my own kernel, and we have the memory management unit working. We also have the kernel virtual separation. We have a little bit of scheduling using round robin, and we also have the block layer working. And currently we are implementing a syncing mechanism to make sure our block layer can be used in a concurrent way, in a concurrent environment, a concurrent context, but not yeah, we still have a lot of stuff to do. We still have to talk to the scheduler and block the interrupts. Those parts are still left. Today we'll try to implement that too. Yeah, let's get into it then. So, what do we have? We have both implementation, and we want to actually add it to our layer. But before that, I also want to put a high level helper that's gonna call the schedulers, that's gonna just mask the interrupts, so that so we have before we do something like a write or read to block, we need to block the interrupts, and then get into the scheduler critical section, do whatever we want to do, release the lock, and then again enable the interrupts. This is what we want, I think so, because if we do it that way, then our critical section will never be scheduled off, and this is something that is important for even for the even for even for our spin lock, not just the mutex. Because initially when we were doing the research, I was like, maybe we don't need mutex because we don't have to overcomplicate it, and let's just implement a spin lock as it's just going to keep holding the CPU and have the lock. But turns out if we are inside a critical section and if something fires up and that fired up interrupt, if that tries to hold the same lock, will be fucked. So yeah, so I believe, I mean, it's a specific case that we may not wanna fix now, but still I think it's still a valid case. Let's just implement that part too. It should be fine. It's not like a real lot of work because it's just one ASM operation and we do have it already here. If we go to our kernel, we already do that, and this is all it is. So we mask it and unmask it. We mask it by putting 0 and unmask it by putting 2. That's all. So before every critical section we can just call that. So we can add a helper that can be called with masking. So these two operations, let's say, are without masking. Let's also add with mask. And add without mask. No. With mask. Unlock with mask. Unlock with. So if we call this, we are supposed to unlock it with this. Let's implement that, and it's going to be the same implementation to. Let's just copy that here from them. And put it somewhere here. And we have to call mask and unmask. Let's write some helpers, and it's going to be static inline mask interrupts. So this is not like a helper, it's going to be just inlined, but for our use case, let's just add it as separate so that it will be a bit more readable, but it will be inlined by the compiler, so we don't have any performance issues. So we mask interrupts by calling 0, and we unmask interrupts. I don't know if we can call it unmask, but we are going to do that. Oh, fuck me. Why the fuck is it fucking with me? Okay. It's going to be 2. Okay. And with mask is just going to call mask interrupts. We call it, and then we call spin lock with lock. We return this. Same thing, we just unlock, and no, we can unlock it and then unmask it. That will be the best way. We first of all unlock it. So results int day to result equals unlock spin unlock. We unlock it, then unmask it, and then return result. That's it. Now we are good to go. So now we also have this operation. Let's just check if our masking is correct, because I remember calling it someone start. So you have to disable them with like this. Okay, we'll try this then. Where's our... Currently we are using 0 to, but it says 0x f, so let's put f. And it's DLF sets, DAF set, DAIF set, and DAF clear. Clear should be fine because that is already copied from there. Okay. Copy from start.s, and we copy it from kmain. What else? I think we are good to go. Now let's try to implement it within our what is it? Block read and block writes. We have block.h and we have block.c. Here, which operations did we consider them? Like there were several operations that we considered as something that needs to be properly held, and I guess this is the one. I think the entire free index can be put into that. Okay, then let's... Is the spin lock included? No, let's include it. And it should be includes core, yeah. Core and spin lock dot h. Maybe if we just put it in here, it would be even better. Spin lock, lock with mask. Oh, we also need a lock. Oh shit. How am I gonna get the lock? Do I keep it as a global lock, or how does it work? So it is a global data. Probably we can have a global lock too. I'm not sure exactly. It's whatever. Let's try. It's going to be spin lock star global lock global block lock. It's just going to be initialized to 0. No, it's a pointer, so I cannot simply define it to... Then I have to initialize it if I keep it like this. Okay, I can initialize it because we do initialize a lot of stuff here. Okay, let's see. It's going to be global block lock, and it's going to be spin lock pointer, and we're gonna k-malloc it with size of spin lock. Okay, and let's also assign it to 0 global block lock. Nobody else is gonna be here at this point because it's gonna be called from k-main. So we can assume that this block is not gonna be held. Nobody else should be alive at this point. It's safe to update this without having to have luck. Okay, and we set the lock to 0, so nobody is using it. I think that is all. We don't need anything else. Inside the find free index, we can just use that lock, and it's going to be global block lock, and we copy that. We also have to make sure if we are returning here, we unlock it. I think we need to use goto here. That is better. Result int 64 results equal to -1. It will be always be -1, and exits. We just set results equal to this and go to exit, and maybe you can also free index This is how we do exception handling in C. And we just return results. If you guys need a real good implementation of C, go look into Python code base. It's just completely C, and I've seen this pattern there a lot, and that's why I know how to do this. And we can just call unlock. So no matter what happens, we'll definitely either come from here or we finish the loop and we come here. So it's the same. And we can pass global lock. So we come into free index lock, we get the lock, we set the result to -1, we do whatever we want to do, and if it happens to work here, and we don't need this, and if it happens to work here, we set the results and we go here and we unlock and return the results. If not, if it didn't work, we would still come back here and we unlock and return results. This is like a finally block. And okay, we have it here. What else? We want to update anything else? What if someone else called the same free index and we are incrementing it thrice, and during this, if someone tries to call the free index and they got the index, we would be overwriting it. How do I fucking solve that? I need to make sure that the person, both sides, agree on something. Maybe we have to put this entire thing into lock, but it's like a really big operation. It's not good. I think this entire thing should be put into that block. And then these operations are fine. And then we need to block this. I guess we're gonna see a lot of races. Yep. I believe so. So let's not block it here. Let's block it here. And unblock it. Unblock it here so that we don't have to have any sort of issues, because the entire operation is blocked and only one person can do anything from here. Lock to make get free index plus use index plus update registers, and we finally come down here and unlock previous unlock the index, used index, and registers. By the time we reach here, these indexes are not going to be used, because we know that we got that index and we can keep using that index. Yeah. Let's just copy this again and put it down inside here, and let's unlock it. Unlock it here. Hopefully we are not using anything else. Let's test this out even without having any parallel execution. Let's see if our lock itself is working, because we haven't yet tested our lock. So it's going to be bash builds. So we have a lot of issues. Fuck me, I didn't even properly write a function. Spin lock.h, spin lock.c, and it's going to be void. It's going to be void. Actually, yesterday I learned that we can have public methods and header file, and still, let's say you have a header file and you have a structure inside it, and you want to use that structure in multiple files, but you don't want those files to actually mutate the fields within that structure, or actually see the definition of structure. Then I thought that there's no other way, because you put the structure inside a header file and you include it inside that other file where you want to use it, and the other file is going to have access to those internal fields, and they can do whatever with it. But it turns out there's a way. You can just put a header file with extern and the structure, and link it using linker, so that during compile time, no matter who tries to access the fields of that structure, they would get an error, but they can use the structure type and other helpers that you have added within that header file. So the helpers would internally mutate the structure, because we are providing that as a service, so we can mutate it. But you cannot directly access the fields from that structure, because it's just an extent, and the compiler does not know what to do, so it will always throw an error. And I saw a lot of stuff that high level languages have that can be completely implemented in C. It's just so interesting. And the model level public and private things, how we can achieve the same thing in C. And inheritance just blew my mind. Achieving inheritance is just so good, and that's exactly how C++ achieves inheritance, but it does, the compiler automatically does for it. So we write the boilerplate C classes, and the compiler finally converts them into how C would achieve inheritance. It's just making sure your structures are placed in a proper order, the fields within. So the child class fields will be copied into the parent class, but they will have a proper order. So you can assume the first block will always be the parent, and the second block will always be the child, and stuff like that. Yeah, I would say C is just the best language there has been ever and written, and I don't think there's any alternatives to C. There's literally no alternatives to C. Rust is okay. I like Rust. I love the compiler. I love those errors. I really learned a lot about lifetimes. But it's just so fucking limiting. There's nothing you can write with valid Rust. Maybe some high level functions. Finally, no matter what, you will have to write unsafe code. And unsafe Rust is just really amazing with the cargo builds and unsafe Rust. It's just C on steroids, I would say, and it's just so good. If I had to write this entire thing over again, I would choose unsafe Rust and write it on it. I don't think safe Rust has anything to provide us, because if you really understand what Rust is, you would simply write unsafe and put a wrapper safe function around it and call it a day, because that already gives you enough idea, because mathematically you can check nothing else can be passed to that function because you have a safe wrapper, and internally you can write whatever shit you want with unsafe Rust. And that's exactly how standard library of Rust is built. The entire standard library is just full of unsafe code, but with a lot of safe wrappers, so you don't feel like you're actually using something unsafe. You feel like you're using everything is safe. But I like the idea of Rust, but it's just once you got used to C, it's hard to go back to Rust. But once you got used to the build system of Rust, it feels annoying to use bash. I don't know why am I even talking about this. I just wanted to say it. Okay, whatever. So here we are. What is the fucking error? So we are converting something. That's not a new error, that's an old error. Only thing we have to fix is that we don't have this file. And why do we not have that file? Maybe we are not in the proper location. Maybe we want to go back one more layer. Definitely possible. Still? Fuck me. I'm supposed to update this. Hey, looks like it compiles. What the fuck happened? Okay, so we wrote. And what happens? Why do we see this operation? Let's go back to our fucking K-main. Okay, I remembered, because we get this extra operations because we actually, so far we never turned on the the actual interrupts. Now that we have turned on it, we are just getting timer interrupts. That's fine. We can unmask it, so we don't have to worry about it, because that's something we can do later. And where is it? Not this. Unmask, mask. Let's just copy this and put it here. I think we have to put it here. I think we would still get some events fired. It's okay. Yep. No, we don't have any. And if I enable it, we would get a lot of timer errors. I mean, it's not timer errors, just timer logs. because the interrupts are firing. I'll just do this and come back here. Okay, it's all good. Hopefully, let's maybe just in case try one more thing. And put this and put this and put this and put Y and put this and get this. Let's build it and let's see if we get something else, and we do get it. So our blocking mechanism works. I think so. It must work because overall it's just the same thing. It should work. Now let's to actually test it, we need to call something in parallel, or at least we should achieve something in a concurrent state. So how we can do it is that we'll have to enable the user process. Do we have a user process already? We have one user context. And what does it do? Do we have two processes already? Okay, we do have two processes. That's simply gonna keep setting one. So yeah, let's see if it works. Let's see if we are actually switching between those first of all. So we need to remove lots of stuff. We can remove this while loop, and then we are setting up all those stuff and we are jumping into it. Yep, nothing much. And the scheduler should handle the rest. And it is working. Because as you can see, here we pushed the process 1 into tail, and currently the next operation is process 2, and currently process 2 is running. Previously it would be the opposite. Here we push process 2 the tail, and the next one was process 1. So the switching is also working, and our scheduling is also working. As I mentioned, it should be working. We tested it a damn long back ago, and things seems to be working fine. So what we have to add is a syscall that is right, that is gonna internally call block read and block writes to a static block, because currently we don't care. We simply want to test if the syncing works. Yeah, so let's see. To enable what is it? To enable syscalls, we need syscall handlers. And currently we have handlers.c, which has a syscall dispatcher, and it has one syscall enabled. That is, if you call 5, then we would get this. And man right is syscall 1, I guess. Let's check it. Syscall Linux write operation. What's the syscall, you fucking piece of shit? What's the syscall number for writes in ARM? And it is 64. 64. So we need to handle 64 here. Okay, let's see. Case is 64. If we have this case, let's first of all confirm if we are able to get inside here. Let's just put a simple print here. Will my prints work inside syscall handlers? I don't know. Oh, but we do have a syscall here, so maybe it will work. Syscall write is called. That should be good. Currently, let's just compile it. Nothing is gonna get fired because we don't have a user function that is calling it. But it is fine. It is fine. Okay, nothing is there. Now let's go into our kmain and go into our user processes. And someday in future we'll have to, because once our file layer is done, we can actually put this user process into the file layer and load it from the file layer and use it. But currently we can't do that because we don't have a file system to start with. So that's why my user processes are already in the kernel context. But they're not running in kernel privileges, they are still running in EL0. Okay, now let's try. We're gonna call write. And where is write defined? Instruction for write operation. Write syscall x64 bit. Okay, this is how it's going to be. One thing is that if we're gonna allocate something in user processes, and if we're gonna give that address here, it's gonna be a virtual address. There's one that only has pages inside the user processes, and from a kernel context, does kernel context have the user level pages? I don't know. I don't fucking remember. But I know that when we actually create the two tasks, we fill in those process table with the actual entries. I don't know if those entries are already existing in kernel context, because kernel has probably the access to that physical range, but it still needs the table entries to make sure that there is some sort of translation. I think so. Well, we'll try. We'll see. In inline clang asm. What the fuck do you mean syscall? I mean, stand lib or anything. My kernel is custom. So, right, should be fully raw. Dun 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 dun. You piece of shit. Raw in inline CASM. Okay, just gave the same fucking thing. Why do I even bother? Okay, so what did it do? We know that the operation has to have inputs, and inputs are taken in registers. And the input register 1 is results. Input register 2 is FD. 3 is buff. How will those input operands map to registers as syscalls take registers as input arguments? So yes, so it's going to be the first argument, the file descriptor for write, and the second argument, which is the buffer, and the third argument, which is the number of bytes write, and the eighth, which is the syscall number. In our case, we are just simply going to handle whatever we pass into the first argument as block reads. So FT does not matter. We can pass whatever we want. We can build on top of it later. Other than that, I think the char buffer seems fine, and count seems also fine. Okay, well, right. So we move the number into x8, and then we call SVC with 0, which is the interrupt for syscalls. And then we pass in output, which is results. And it's not going to get a separate register because we haven't used ampersand. And then we have the inputs, which is going to be FT and buffer and the counts, which is the size. And then we are going to say that we have clobbered x8 and memory. Why do we have to specifically mention x8 here? Because we so far only mentioned memory, then why do we have to specifically mention x8? Maybe to state that we should not update x8. Maybe we are saying that these are the important operations. I don't know, let's ask, why do we have to specifically mention x8 as clobbered? What does specifying clobbered actually mean? Achieve internally. Okay. So it's a compiler primitive. We're just saying the compiler that this is updated. So it prevents from register allocations and shit. So it's a compiler primitive, it's not a runtime primitive. Leave that, it doesn't matter. We're not compiler engineers yet. It's just a fucking goddamn hard field. We'll come back to it when we are old. Right now we are gonna simply write a syscall handler and we're gonna put it under what? It's going to be syscall dot h, and it's gonna if and f syscall define int okay, we have the definition. Let's write the signature. Its signature. All the syscalls are supposed to return int. Let's see, int 64 includes std_int.h, and then we include int 64. Let's put 64. I don't know why we need 64, but we'll put it as 64. And then we need sys write, and it's gonna take a fd, which is gonna be uint 64 fd, and it's gonna take char buffer, and then it's gonna take fd, char buffer, and size, and it's going to be char star buff, and it's going to be size. Size, which is the number of bytes. Output will be either -1 or the number of bytes written. This is the only syscall that we are gonna currently support. So let's deal with that first of all. And we can write syscall.c, and we can include syscall.h, and we can start writing int 64 syscall write, and it's gonna be int 64 ft char star path and uint 64 size. And the internal implementation is we always written -1. There's if something goes wrong, or we can call, what is that? We're gonna call, what are we gonna call? Are we gonna write in line assembly? and it's going to be some volatile and we need to move what's x8 64 and then we are gonna move and then we're just gonna call SVC. I think it's just SVC. That's it. And then we can say output equal to, we need output variable, so it's even 64. No, it's int 64. Results, and then we have inputs, which is the first register, which is FT, and the second register, which is going to be the same, and but it's going to be a buffer, and we have the third register, which is size. And finally we are going to set that we are going to be clobbering X8 and we are going to be clobbering memory. Maybe we return results. That is it. Perfection. Now let's try to call it. We go to kmain and we are inside core, so I think we can call syscall and we can call, what is it, syswrite and it's gonna be an FT, which is simply 1, and we need a buffer. Let's allocate a buffer in stack char star test, and it's gonna have 5 characters, and we just put it as 1 and 2, 1 and 1, 1, 1, 3, 4, 5, yes. And we're gonna pass test here, and then we're gonna call the size as 5, and we're gonna have int 64t results equal to that, and we can put a result of write. It's currently going to be nothing, so hopefully this does not crash. Maybe we don't want to write it because I don't know, because currently we don't return anything, so maybe it will crash. Do we return anything? Let's go back to our handler and see that. We go back here. Okay, result is just 0. Okay. I think then we can just write. And we come back here and we can write %L just go back to our build file and add the new files here, and it's going to be core syscall.c, and also here syscall.o, and it should be good. Bash build. The fuck? Conflicting types? Oh, it's units. Okay, we have some conflicting types that we need to fix, and we are good to go. I'll put you in here. And if we build it again, why? Now the error is just that invalid inputs. Do we need to put equal to? Maybe that is the one. When we are in the first time, we are inside task, initted to tasks, jump into task 1. Oh, you mean task 1 did not finish? Task 1 is running. Do we get that? We get task 1 is scheduled. Maybe we didn't give it enough time. Search is yes. Oh shit. I forgot how to say search within Tmux. Okay, guess we have to go the other way. We can build it. Fuck it. Oh, it's so fucking annoying. And let's see. I don't like this entire logs. I'm gonna remove them and see to it. If we go to scheduler.c, we have a lot of puts. We don't want any of it as of now. We're gonna just and we also have to remove the timer interrupt log. And where must that be? I don't know. Let's see. It's here. Okay. I don't want that. Now, if we compile it, we should only have a little bit of. I don't like this read back, setback. What the fuck? Where do we put that? What the fuck? Maybe it's in scheduler. I removed everything, right? Okay, I have this here. And anything else? We should have one debug flag which will directly enable and disable them. It would be really good. Now when I want this back again, I'll have to again enable every damn thing, and I'll be annoyed at that time. It's sad. What the fuckity is this? Setting back. Oh, it's inside timer. Task 1 is scheduled and then nothing happens. That's not good. Jumping into task 1, we see that as the final message. Where is that fucking message? I believe it should be incoming. Yeah, we are here and we jumped here. And task 1 did not run at all. That's not good. Okay, it's not running at all. Maybe we fucked up something in the process of commenting out stuff. Let's go back. Go to handlers. Okay, we didn't touch much in this. It should be fine. And we don't get this either because we're not even jumping into the process. So that's a completely different issue. If we go to scheduler, we unblocked this. Yeah, unblock this. My code is the most disorganized code I have ever read. Well, whatever. We have GDB. We can try it there. It's simply not supposed to do that. We'll build, run it, kill it. Vi camo. Okay, it only has this logs. We enable all of them. Disable this. Kill it. Shit show. I kill it and run it. What the fuck happened? With logs, it's just the entire execution feels completely slow. It feels like I'm watching it in slow motion. Because if you just remove that logs, it's like instantaneous. Okay, we jumped. Okay, we have a far exception. We are in EL0 to EL1 and we are at this location and we tried to read this and we don't know what that is. And that's exactly what I thought is gonna happen, because we are inside kernel contexts and we are switching back. No, we are inside user context and we are switching into kernel context, and from kernel context, if we try to read a user buffer or anything of that sort, we're gonna fuck it. But I have one question. Why the fuck? Why would it happen now? Because this, at least this should have printed. I mean, there's no, I mean, if this failed like this, it makes sense. Oh, why the fuck did this fail? Maybe it does not have access at all. Let's remove those stuff. I don't know if it has the table entries for that UARTs. Looks like there's no errors. Let's double check it. Okay, so there is no error, but then what I have to confirm is if we actually call the syscall at all, we can go into our what is I don't see this message either? Okay, then let's go back to our vectors. Let's see. Here, if we come back, we should have EL1 sync entry. This is what I think we need. And we are comparing it with 0x. X1 fine. No, I don't seem to have reached this point. Well, we have one option, that is disassemble EL0 sync entry, and we just put breakpoints here and we run it. We don't see it, so it's not happening. So what we can do next is we go to kmain and take user process and stop there. Break user process. No, we'll disassemble user process. User process 1 and we break here. We also update it because when we are in virtual namespace, we go in and we didn't. What? Okay, let's do that. We can somehow we are dealing with multiple errors, not just one error. It did not stop at that location. Why is that? Jumping into task 1. Let's see. Optics. Let's see. Let's try this number. Disassemble. There's nothing that. Maybe because we dynamically allocated. Okay, then let's do this. Disassemble key main. Stop here. And okay. Mesh build. Okay, we are inside that. We jump into it. No, we are actually in this function. We're not sure. We're not supposed to confuse it because we are in this function. And as a definition. Okay, it is in vector.c. And here, so we do all those stuff. So okay, let's just do everything. We're just restoring registers, updating things, and finally we say erits. This is where we jump into the user process. Okay, we are inside the user process and it starts here. And because why we are not able to stop here, probably it's because of the table entries, and this table entry is probably pointing to something completely different. So we also have to think about that. That's why it didn't break there. Let's try moving. Okay, finally we have the sys rights. And this is where we are getting fucked. We don't have access to sys rights. That is true. That is true. Because sys rights is defined within kernel contexts. And as you can see in my task init, I only map this entry. Probably I also have to map the write function to the entry so that it will have access to its. That's gonna be a lot of work. So let's just write it down. To do currently this write is not in the users table, is not mapped in the user table. We have to map that and try again. Currently we just get table false when we jump into this right. But we have defined implemented this right and called it here. That is good. So overall what we have done today is that we have we only managed to integrate the pin locks into our system, I mean into our block read and block write, and we also tested it. It is working perfectly. There's no undefined state. As long as we properly get the lock and unlock it, it should be working fine. And we also have added masking and unmasking so that the scheduler will not interrupt us in middle of a critical section. And other than that, we started to look into the user processes and how to test this. And we added one syscall, and it's syswrite. We also managed to see how the structure of syscall should work and what is the syscall number and stuff like that. And it's all good. So next week, let's try to actually implement the, I mean, actually map the syswrite into user processes, because uh, it has to be inside the user process memory for it to be able to understand it. Yeah, that was the actual issue, nothing much. Okay, actually we can try it quickly, because if we just copy the assembly and put it here, that would be a shortcut. Let's try it next time. Okay guys, thank you. I will see you next week then. Bye bye.